Hey, this is chapter 2.7, use absolute value functions and transformations. So once again, we'll be using the concept of the parent function, that which is the most basic in a group of functions, which you'll probably remember as being f of x equals x for a simple linear equation. And now, since we're talking about absolute value, the parent function is f of x equals the absolute value of x. So when we graph this, we get this graph here, which is the blue graph, and it makes sense because if you remember the definition of absolute value, so say we plug something into this equation. So we have basically y equals absolute value of x, and we plug in y equals, let's say, the absolute value of -5. So the absolute value of -5 would just be 5, right? So no matter what you have as your x, your y is always going to be positive. So that's why we have a V-shaped graph, and notice that the whole graph is in the positive y range, and so no matter what our x domain is, it can be positive or negative, but y will always be positive. The graph is also symmetric about the y-axis. As you can see, these are mirror images of each other, these two sides of the graph. And if we want to plug in 2 points, so we have these 2 points in red, and say they are, the graph is not to scale, but say they're 3, 3, and -3, 3. If you plug these in, we get 3 equaling the absolute value of 3, and 3 being the absolute value of -3, which makes sense. And then once again, or not once again, but pretty obviously the vertex is 0, 0, because if you plug 0 in, you get 0. So, transformations and translations. This you'll probably remember from geometry, as it says above. But now, instead of transforming and translating geometric shapes such as squares, rectangles, triangles, we're going to be transforming and translating equations. So if we have our graph here and our equation, so we have a line, and we want to translate it 3 spaces to the left, that's going to be a horizontal change or translation. So as you can see here, a translation is a horizontal or vertical shift. So we would move this shifted to the left. That would be a translation. For a transformation, that changes size, shape, position, or orientation. So we could have instead, let's use another example, we could have a parabola. This is our original parabola. And if we were to make it a skinnier parabola, that would be a transformation. Now we can see this in the equation for the graph. So the graph takes the form of y equals the absolute value x minus h, closed absolute value, plus k. So h and k stand for the vertex, as is shown here. So for our formula, we could have y equals the absolute value of x minus, let's say, 5, plus 6. So our vertex would be -5, 6. And that's actually a common mistake people make because the base formula has a negative sign in it already, so therefore the h does not include the negative sign, if that makes sense. So we're going to translate the parent graph h units horizontally, so h units horizontally, and k units vertically, plus k. So the h is horizontal and k is vertical. So we're told to graph y equals the absolute value of x plus 4 minus 2, and then compare it to the graph of y equals the absolute value of x, or the parent graph. So this one here on the left is the graph of y equals the absolute value of x plus 4 minus 2, and the one on the right is the parent graph. So when comparing these, we can see that, first of all, this one on the left has a vertex not on the origin, where this one does. And when looking further, we can actually see that it's been shifted 2 to the left, so 1, 2, and then down 2. or down 1, sorry. Whereas this one is completely centered. Therefore, we know that this is a translation, and we can actually look back to the equation to see where this comes from. We can see that 4 values have been changed. So actually, these 2 steps here, 1, 2, each of them is 2. So it moved to the left 4 total. 2 plus 2 equals 4. And since there's a plus in the absolute value signs, it actually means that it moves to the left or to the more negative direction 4 times. Rather than a plus, you actually take the opposite of that and you move in that direction. Whereas the 2 is outside of the absolute value, so the negative remains true and we move down 2. So next we have stretches, shrinks, and reflections. These are transformations, so instead of just shifting our graph, we're going to be stretching it bigger, shrinking it, or reflecting it, as we've just said. So we can know this is happening when there is a constant in front of the x value. And this is telling us by what multiplier we are going to be changing the width of the graph. So say we have an a value and the 3 is our a, that is greater than 1. The graph will actually shrink in width. So if our parent graph is this graph, our graph here will actually be shrunk. So vice versa, not vice versa, but with the same logic we can apply to this graph to the right. Sorry, I should have done the blue one in red. The one on the right will actually be wider. Even though it has a smaller constant, it will be wider than the 3x. And I can explain this algebraically as well. Now a reflection, so once again we have our parent graph here. Our reflection will be the negative of, well, okay, I'll explain it this way. If we have a value of 5 as our x, then y is the negative absolute value, so it will be reflected over the x-axis and be here. So now that we've covered both translations and transformations, we're going to be combining them both into one equation. So we're going to be using the full form of y equals something x minus h plus k. And this something is our constant multiplier, so it's a, as we've just covered. So in our example, we have y equals negative 2, the absolute value of x minus 1 plus 3. So we start with our parent graph and we transform it from there. So our parent graph, we have our axes, and then next we're going to draw our parent graph, like I just said, sorry. And then first we will transform it, or we will translate it 3 spaces vertically. So next, we've moved our graph 3 spaces vertically. We need to move it to the right 1 space, and I'll copy down the problem again. Equals negative 2 x minus 1 plus 3. So x minus 1 plus 3. So we've already taken care of the 3. And now we need to do the x minus 1. But since it's an absolute value, it's not moving to the left one or negative 1. Rather, it's moving to the right one. I know this seems counterintuitive, but you have to get the hang of doing the opposite of what seems to be what you're supposed to be doing. So next, so this is the graph after it has moved to the right 1 space. And finally, we need to multiply it by the multiplier of negative 2. So we are going to, the negative, remember, is mirroring it or reflecting it about the axis. So we need to flip that. After reflecting and then shrinking our graph, this is our final answer. This is our final graph.